Hello everyone. This video is to give you an idea on how to do the exponential growth project, your first project. And so what I'm going to do is quickly explain what the formula means, as well as how to get these calculations. So basically what you're asked to do is to see how money could grow over time by using what's called an exponential growth function. And of course, the function that we're given here is what's called the exponential growth function, where interest is compounding continuously. And so it's called the continuously compounding exponential function for short. Now, to explain what this means, or what these variables mean, this p sub 0 is what we call the initial amount, or the initial principal. And so here, if you notice, I've used 15,000. For your project, you need to use another number like 7,000, 20,000, 100,000. I just ask that you don't use 15,000 because I'm doing it here. Other than that, the K that you see here, this K that's right there, is your actual interest rate, and that is annual interest rate. So here you'll see that I have K is equal to 0.5%. Now, of course, in decimal form, that is 0.005. And here this is 1%, so that would be 0.01 if I was putting it in pure decimal form. And let me clean that up. And if this was 1.5% in decimal form, that's 0.015. Now T is time, and time that will be in years. And so if you're given time that is in fractions of a year, then you would have to do a fraction of that. So let's say if you wanted 6 months, that would be a half of a year. Or if you wanted 3 months, that would be 1/4 of a year. Okay. And this number E here, E is what's called the base of the exponential function, but here it's an irrational number that's actually approximately equal to 2.712. And so all that we want to do here is, for each percentage amount, we want to see how this $15,000 will grow over time. And so we want to do this when T is equal to 1, meaning 1 year. We want to do it when T is equal to 5, which is at the 5th year, and we want to do it when T is equal to 10, which is if we let that money grow at a continuously compounding interest rate for 10 years, how much would be in the account afterwards. Now, I'm going to start off with this first one here, and let me just kind of underline all this so we know where we are. So what I want to do first here is calculate what this would be for the first year. So if T is equal to 1, then here this would be P of 1, which will equal to 15,000 times E raised to the K, and K in this case is 0.005 times 1. Okay. And so, of course, we can put this in our calculator to figure it out. And so I'll do that once I'm done doing these others. So here for P equals 5, same thing. Just 15,000 E raised to the 0.005 times 5 in the exponent. And then for T equals 10, we'll just do 15,000 E raised to the 0.005, and that will be multiplied times 10. Now, to make this real simple, we can put this into our calculator. And so to put it into our calculator, the easiest way to do it is to just tell the calculator to come up with this function here. And so in general, for what we'll be doing here, in this example, our function will be P of T is equal to 15,000 e raised to the 0.005t. And of course, when we go to k equals 1% and k equals 1.5%, we'll change this number right here, but keep everything else the same. Okay. So this is what we will be using. Now I'm going to erase this and erase this so that I can put all of this information up here, so I'll have some room. And so now what we want to do is actually go into how we put this into your calculator. I am using a TI-83 Plus emulator to do that. There's several different ways that you can install an emulator on your laptop or phone. If you have an Android phone, the easiest way to do that is to use the app called Wabbit EMU, meaning Wabbit Emulator, and you can just download it. If you have an iPhone, I think there's a version for that as well. And if you have a PC or laptop that is not a Mac, then of course there is a Google site that you can go to that has a pretty good emulator, and it'll pretty much download without any issues. So however you get the calculator, or if you actually own one, then if you follow the steps that I'm doing, you'll kind of see that this is real easy to do. Alright, so I'm going to bring in my calculator here, and what I'm going to do is just type in this function, the 15,000 times e raised to the 0.005t. So I press the y equals button, and then I do 15,000, and then I don't have to do this, but I'm going to do it anyway for clarity. Say times, and then the number e, you may not be able to see it, but the number e is right above the division sign, and there is a function e raised to the x that is above the ln or natural log button. I am going to use the e raised to x because I have some other things I need to put into the exponent. So here to get that, I have to press yellow, and then you see how it says e raised to. And now what I want to do is type in 0.005 times, and now here this button is the variable button. And so this is the button that the calculator uses to say, all right, what are you going to be changing numbers with? And then I close a parenthesis to make sure that all this is in the exponent. Okay. Now, the only other thing that I need to do here is I need to go to the window, and I need to make sure that the values for t that I'm going to use, in this case it'll be x, can go up to 10. If you notice here, I have my x-min at -10, my x-max is 10. So 1, 5, and 10 can definitely fit in between -10 and 10. I normally like to go a little larger just in case I may have to use it for something later. So I'm just going to put mine from -20 to 20. So now from that point, all I do is I need to get to this calc feature that's in yellow. So to do that, I hit the yellow button, calc, and then I go to value. And then here you see how the x equals pops up. Depending on your calculator, this may take a while, but as soon as it pops up, the only thing that I need to do now is type in 1 for 1 year. And if I do that, you'll see that I get the answer $15,075 and about 19 cents. So that's what that is. So $15,075, 19 cents. And now I need to do the same thing for, so after I do it for 1, oops, let me go back here. So clear that. So after I do this for 1, I can go in directly again and just type the 5 and then do it for the 5 year. So in other words, our $15,000 has grown to $15,379 and about 73 cents for the 5-year mark. And then I can do the same thing for the 10-year mark. And you see now it's grown to $15,769 and about 7 cents. So this is what we need to write here. So I'm going to go ahead and just write those numbers. Let me go ahead and do the calculation for 5 again. And you see that that was $15,379 and about 73 cents. And for the one where it was 10 again, so for 10, that would be $15,769 and about 7 cents. Okay, and so that is what those calculations would be. We see how the money grows over that 10-year period. But of course, since it's a low interest rate, we've only gained about almost $770 over a 10-year period. So that's not that attractive. So what we can do now is let's increase the interest rate from 0.5% to 1%. And then we can see how the money will grow then. So to do that, let's bring the calculator back. Let's go to y equals. And now instead of having the 0.005 here, we're just going to have 0.01. All right, so to do that, we need to come here, and I think I hit something, so I'm just going to get it back to the way that it was. All right, so it looks like we have it back the way that it was. So here I'm just going to change this from 0.005 to 0.01. So to do that, I'm going to come here, and that's what happened last time. So let me try to fix that. All right, so let's see if we can move this back. And what I'm going to do is just basically change this number here. So I'm going to get rid of that 0. And then I'm going to change this 5 that you see blinking there to a 1. And so now that should be in the exponent 0.01. And this should be times x. And so now, once I have that, then of course, I can go in and calculate values for P of 1 when K is at 1%, P of 5, and P of 10, meaning what is going to be the amount after 1 year, 5 years, and 10 years. And so, of course, I'll go in, go to calc again, so second, trace, number 1, have the x equals. So now when I hit the number 1, you see now that I have $15,150.75 after 1 year. Very different from here. So because the interest rate doubled, you saw that the amount of extra interest I earned within 1 year just about doubled as well. So if I do it for 5, I just hit 5 and then enter. Then of course you see now I have $15,769.07. That was the same amount as I had in the 10-year period. So because my interest rate is twice as much, I'm earning money twice as fast, basically. That's the interest on it is earning twice as fast. And then of course at year 10, you see that now I get to $16,577, and we round that to 56 cents. So we'll go ahead and record these values here so that you can see the difference over time. So I'll just go ahead and write these down. I won't write the formula this time, but we know here on this one, P of 1 is going to be $15,150. And let me go back and actually get that amount there. So let's make that look a little more clean. Yep, so we'll get rid of all that. That'll be $15,150.75. And then, of course, at the 5-year mark, we know that that's $15,769.07, approximately. And then at the 10-year mark, we'll go ahead and calculate that again. And that is $16,577 and about 56 cents. Okay. And so now you can see how with the interest rate being doubled, how the money is growing much faster. Now, bringing the calculator back, we can do the same thing here for the 1.5%. And again, all we need to change is that value K, in this case from 0.01 to 0.015. So we'll go back to the y equals, and we see that here in the exponent, the 0.01. Now we're going to change that to 0.105. And so how I'm going to do that is I can insert a number here. And of course, if you see above the delete key, you have the phrase NIS, which means insert. So I can hit second, insert, and then there I'm going to put a 5 there. And so this reads now 0.015, which is exactly what I need here. And so everything else will stay the same. I do my calc feature again, second, calc, value, and then I calculate the values again for 1 year, 5 year, and 10 years. And so I'm just going to do these in the calculator. I won't write these down this time because now you probably have an idea of what's going on. So at the first year, we hit it, enter. We see that we're now $15,226 and about 70 cents. And of course, that's way more than the $15,075 or the $15,150.75. At 5 years, now we're at $16,168, so almost as much as what we had here at the 10-year mark, because we increased the interest rate by almost 50%. And then at the 10-year mark, now we have $17,427.51. So in essence, this is what the first part of the assignment is asking you to do, is to be able to study these particular amounts over time based upon the interest rate. All right, so after you do these calculations, the second part of your project involves you making a report that includes such things as your actual calculations. You want to know what effects did changing the interest rate have on the rate at which your investment grew. And so you kind of seen that as the as we increase the interest rate, of course, the money was growing faster over time. We also want to know, all right, well, what effect did your interest rate have on the doubling time? Okay, the time until your initial deposit doubles in size. And of course, we didn't do that here, but I'm going to do that next. Show you how we can actually find the doubling rate. Okay, and so we can find it on our calculators as well as find it by doing it mathematically. So we want to know that, and then we want to assume that this money is being invested into a savings account. And you have a question saying, are there interest rates that we selected here? Are they realistic for today's accounts? Okay, and you need to give a reason why or why not. You also want to consider the formula that we use to determine the future value for our deposits. Okay, is the formula a realistic approximation of what you could expect from an investment or are there other issues and factors going on? Okay, and so the formula that you use is what's called a continuously compounding accumulated interest formula. So this is like saying that you're earning interest every moment, every just every little nanosecond of the day. And I can tell you, realistically, that's not going to be the case. But if you're being charged or if you're being awarded interest, let's say on a monthly basis or more, it's almost the equivalent of that. And so you can say what you want about that. You're also asked to say, besides savings accounts, what other kinds of investment accounts or programs are typically offered at the bank where you are a member at? And do these accounts use compound interest? And what are the typical interest rates there? And then, of course, the last thing that you're asked to do is to use the textbook that you're using or another reference to research how to calculate simple interest. And so, given what you know about compound and simple interest, which would you prefer that your investment program do, and why? Okay. So all those things I can't really answer for you because it sort of kind of takes your perspective and your opinion on it versus whatever it is that you end up finding. So I'm just here to show you how to do the computational part of it. And then, of course, everything else is sort of critical thinking, and you can kind of put something together for that. So I hope that what you've seen here actually helps you to be able to get started here. The last thing that I want to do is show you how we would find the doubling time. And so I'm going to do this for the 0.05% example as well as, sorry, the 0.5% example as well as the 1% annual interest example. So the easiest way to do this is we're going to, of course, find out, well, how much money is it if it's double whatever amount we're talking about. In this case, since we're using $15,000, of course, $30,000 would be the amount that we would have if we were doubling our money. Okay. Now, an easy way to do this is to go to the y equals again. And so now what I want to do is enter another function. And since I'm using 15,000 here, I'm going to go into the y2 area and do 30,000. And I'm also going to go back to here and change this to 0.005 so that we'll have what the original interest rate was. And what the calculator is going to do now is actually graph this as well as graph this function, just the 30,000. And the 30,000 would just be a horizontal line. And we're going to ask the calculator to intersect, to find the intersection of those two functions. So when I graph it, it'll look, I guess I don't really have the window here, so let me go ahead and set the window to something that's realistic. So here, let's start at 0, and let's go to, let's say, year 15 for the y-min. Y-min is actually going to be the lowest dollar amount. So I'm just going to say, since the lowest amount is 15,000, I'm just going to do 14,000. And we know we want to go up to 30,000, so I'll just give myself a little room to go up to 35,000. And we can graph this. Okay. Now, if you notice here, because of how this looks, this is the 30,000, and this is my other function. If you notice, they have not crossed yet, so that means that the window I gave myself, horizontally speaking, isn't enough. So here I'm going to go and say, all right, well, let's just extend this, and let's just get real crazy and say 100 years, and let's see what that gives us. Okay. And if you see here, it's getting close, but it still hasn't got there. So we're like, wow, that's going to take a while. So let's go to, let's say 150 and graph. And then you see right here is where it intersects. So now this is your exponentially increasing function for your money here. This is the $30,000, and we want to figure out where this intersects. So to do that, we go to the calc feature again, go to second, calc, and then here, instead of picking value, we're going to go here to number 5 and pick intersect. And so you can either press the number 5 or scroll down to 5 like how I'm doing here and hit enter. And so when it asks you these questions, it'll say, what's the first curve? In other words, this is this function here. We'll just say enter. The second curve is going to be your horizontal line, 30,000. And then we want to guess where the actual intersection is. So I'm just going to keep clicking until I get there. And then that's close enough, and I hit enter. And then you see that the X value there is 138.62944. So we'll just round that and say 138.6 years. Okay. And so if we put our money into an investment that earned 0.05% annual interest per year, compounding continuously, we would have to wait almost 139 years to have our money double. Okay. So that is probably an issue for you, being that most of us, or any of us for that matter, do not live to be 139 years old. Okay. So here for the doubling time, so we'll just say this is T double. We know that's approximately 138.6 years. Okay. Now we'll do the same thing for the for whenever our interest rate is 1%. So to do that, we can go to the y equals button again. And so now we need to change this number here from 0.005, 0.01. So just like how we did before, we're going to delete that 0 and change that 5 to a 1. And so now we'll do the same thing. So we'll graph. And we see that, of course, it goes up a little faster, so the intersection happens a little quicker. And now, second, trace the number 5. And then here we go through the same thing again with the intersection. So here we have first curve there. The second curve is the horizontal line. And then we want to guess where they intersect. That's close enough. And so we see that the actual intersection is at about 69.314718 years. So just roughly about 69.3 years. So of course, we'll just say T double here is about 69.3 years, which is much faster than 139 years. So we'll do this one more time, bring the calculator back, and we'll do it one more time to do when we have 1.5%. So let's go back to y equals. We are here, and we need to have 0.015. So I'm going to do second, delete to insert. I'm going to insert a 5. And then after that, I graph again, and you see that it rises faster. And of course, the intersection is even closer now. So we'll do second, calc, intersect, and then the first curve. Can't see it, so try to figure out where our cursor is here. Yep, so our cursor is there, so that's our first function. Hit enter, and then the second is the horizontal line. And then we go here to figure out the guess for the intersection. So now it's there. And so here, 46.2 is about how long it would take our money to double if we had it in an account that was earning 1.5% interest compounded continuously. Okay. All right. So the very last thing that I'm going to do is for this last one here, when we have 1.5%, we're going to show you how we can actually calculate that mathematically, but without us having to use our calculator to do the whole intersection thing. So I'm going to make some room down here, and I'm actually going to work out this equation for you so you can kind of see how this works. So of course, our function here, if we use that, is 15,000 e raised to the 0.015 t. And what I want to do is find out what t is when p of t is 30,000. And remember, for you, whatever your number is, whether it's 7,000, 5,000, 100,000, whatever, your p of t is going to be twice that amount. So if I do that, I'll have 30,000 equals 15,000 e raised to the 0.015 t. And of course, if you're trying to find the double time for the 1% or the 0.5%, this number here would change. First thing I want to do is divide both sides by 15,000. And in doing that, I know that this reduces to 1, and I just have e raised to the e raised to the 0.015 t. And here 30,000 divided by 15,000 is 2. Okay, so from that point, we have a couple of different ways we can go about this. So one way is to just take the natural log of both sides. That's one of our logarithm properties. And so if we do that, then of course on this side, natural log of 2 is just a number, so there's not much we can do with that. But over here we have natural log of e raised to the 0.015 t. And so natural log is the same as log base e. So really this is what you have. And one of your logarithm properties says that anytime you have log base a of a raised to the x, we know that that just equals x, which is the exponent. So here if I have natural log of e raised to the 0.015 t, all this is just 0.015 t. Okay? And then from there, all I have to do is divide both sides by 0.015 t. And now all I have to do is put the natural log of 2 divided by 0.015 t in my calculator, and I'll see that I should get that value that's same value that I got whenever I was doing the whole thing with the intersection, which was about a little over 46 years. So to do that, we'll have natural log of 2 divided by 0.015. And you see that I got a little over 46 years. So that's how that can actually be done mathematically. Again, we can do the same thing by changing this number here to just 0.01 if we wanted to figure out the doubling time for the 1%, and same kind of thing for the interest rate of 0.5%. Okay. Now, one thing that you'll see in common no matter how you do this is there is a pattern that happens. And so one of the things that we know is that there is a direct relationship in between the time and the interest rate. And so here I'm going to write it this way. And so here, if we are going to double our time, then we know that, of course, the interest rate times the time is always going to equal natural log of 2. So what that means here is that if I wanted to figure out the doubling time, it's always going to be natural log of 2 divided by whatever the interest rate is. Okay. And similarly, if I wanted to figure out what the interest rate was, I would take natural log of 2 and divide it by the time. Now, if I'm doing what's called half-life, or I'm trying to figure out how something reduces in half over a certain period of time, the only difference now is that this will be negative, okay? And that's true because when we are basically exponentially decreasing, this k right here would be a negative value as well. And so if I was to take a negative divided by a negative, I would get positive, because time always needs to be a non-negative quantity there, okay? But other than that, that's pretty much it. Now that you know how to get the doubling time both in a way of using the calculator as well as computing it mathematically, you should be able to do this project with no issues. So just email me or give me a text if you have any questions. Take care.